Hey, today I wanted to talk about a certain section of mathematics, statistics. Now, statistics, I remember in high school, people would say, "Oh, do you want an easy class, an easy AP class? Take AP Stats. It's a free ride." And even in the math community, something like a stats degree is seen in undergraduate degrees especially is seen as like, oh, it's an easy math degree. It's not really a math degree, it's a stats degree. But it's its own field of mathematics, really, that has its place, and that's a really, really useful place. So I wanted to just go over a bit of the basics in this kind of longer video, have it separated into a few different sections, and that way provide a sample of probability and statistics, and hopefully give people the nudge into it without having it seem either intimidating to some or like a joke to others. Now, when starting to think about stats, one of the first things we talk about is probability. But before we can get to that, let's get to some visuals. Let's look at this rectangle here, and we'll call this rectangle the space S. Now, what's actually in S? A bunch of random stuff, but two things we care about are these two sets. One we'll call set A, one we'll call set B. Pretty simple. Now, when you have set A and B, we want to talk about how they relate to one another. So, as we see this Venn diagram, there's a few things we can notice. Start with, we have this section of A takes up a big chunk, section of B takes up another big chunk. As we can see, we've had this section in the middle, which you can kind of see in the purple, that they overlap. So, if I wanted to talk about everything we have here, let's talk about the set A and the set B together. We would say the union of A and B, represented by this kind of large U. And we could color code this, be like A unioned with B. Alright, so it's all the things in both of them. But what if we only want to look at that space in between, the intersection? Well, we could write that as A intersected with B. And the way to think about that is only the purple spot, right? This place where they cross over. Not too bad. That's a pretty simple representation through a Venn diagram. It's pretty nice. Alright, but now let's think about, what if we have, this space S, and this time we're just going to look at one set that, again, we're going to call A. If A is everything inside of this set, then what about the stuff outside of the set? What about everything else? Like, think about it as a sheet, and we want to cut out A and just take the rest of the sheet. A little visual here. Well, we would call that the complement of A, denoted as that. Now, that's pretty simple, complement A, everything outside of it, but something to think about is that if I have a second set, B, well, B is partially in the complement of A. And so when we have to look at these relations, we have to think about how much is in one set but not in the other, and it gets pretty interesting from there. Alright, but what if, let's look at another situation. S again. A and B. This time, they're not even touching. They don't intersect at all. They share nothing. So, a way we can denote that is saying that A intersected, let's make that a bit better, A intersected with B is equal to something we call the empty set. Because if I say, well, all the stuff in A crossed over with all the stuff in B, there's no purple. There's no spot where red and blue mix. There's no spot where A and B mix. So, it's empty. It's nothing. Now, it's not too far of a leap to jump off of what we've previously mentioned. Okay, S, we have, say now, 3 sets. A, B, C. Well, red, blue, we'll say, do I have yellow on here? We'll say orange. Well, you have some places that they cross over, right? We have A and C crossing over, B and C crossing over, and A and B crossing over. And if we want to look at the places where all of them are put together, that would be as simple as saying A union B union C. Okay, what if we just want to look at the place where they all cross over right in the middle there? A intersect B intersect C. Alright, and with that, it's obvious, it's not too far. It's pretty clear that you can say, what if I want to just look at B and C's intersection, or just the combination of stuff in B plus the combination of stuff in C? I could go B union C for the combination, the union, or B intersect C for that intersection. Alright. Not too bad, not too crazy. So let's put some numbers behind all of this. Alright, if I'm looking at an entire set, and I want to say now, what's the probability of that set? What's the probability that if I choose an item in this set, it's in that set? Well, it seems kind of ridiculous to say it out loud, but the probability would be 100%. But we denote that in a different way. We denote it by saying P of S, our set, is equal to 1.0. Because instead of 100%, we'll talk about probabilities in 1 being 100, 0 being 0, and the decimals being our percentages. With that, we can say that in this set S, if I'm choosing from A and I'm choosing from B, well then we're going to have a probability of A be something, we're going to have a probability of B be something, we're going to have a probability of A unioned with B be something, we're going to have a probability of A intersecting with B be something. So you have all these different things, and now remember also, we had a complement, everything outside of A. Probability of A complement, probability of B complement, probability of, if we're just looking at the intersection, what about everything outside of the intersection? A unioned with B, or sorry, A intersecting with B complement. It can seem like a lot, and it can seem like a lot of funky notation, especially when, again, no numbers behind it. So, we're going to go ahead and take a look at that next. Alright, let's take a look at how different things within a space and these different combination of sets can interact with each other. Our usual setup, A and B, they have an intersection. Now, if say the A section here takes up a certain percentage of our square. Like, probability of A is equal to 0.25. Okay, well then we also know that B here takes up a certain section of our square. The probability of B, we'll say, is something like 0.40. Seems reasonable enough. Now, what would the probability of their union be? A unioned with B. So, initially, you may just think, well, let's just smash them together. That's what it means, right? We're combining this one and this one, so the probability should be added. Almost right, but not exactly. We're missing something. Let's go ahead and write out this with some more diagrams. Always fun. So, gonna say, not even gonna do this whole thing. Let's make it. Okay. A plus probability of B. You notice though, there's something we're double counting here. Probability of A plus the probability of, there we go, probability of B. The crossover point, this intersection, we account for it twice because it's in A and it's in B. So, we should remove one of them. Let's say minus 1 probability of A intersected with B, which we'll do this part in purple. That chunk there, we need to remove one of those because we have two. So that gives us the formula, the probability of A unioned with B equals the probability of A plus the probability of B minus the probability of their intersection. So earlier we said that A was 0.25 and B was 0.40 for the probabilities. So let's write these out. We get 0.25 plus 0.40, and we'll say the intersection then is something like 0.15. That feels reasonable. Well then, the probability of their union would be, well, 0.25 plus 0.4, we get 0.65 minus 0.15 equals 0.5. And that becomes our answer. Not too bad. Let's try some more stuff. So jumping off what we just did, this formula we just made, let's try and find out how we would discover the intersection. Ooh, I can make that look better. There we go. The intersection of two sets. For that though, we would need to know the union already, the probability of A, and the probability of B. So let's go ahead first and rearrange our formula and then plug in some values. Now, this is something that people tend to overlook in math, and that's you're given the pieces to find things, you need to play around with them. We have all we need to rearrange this formula to get an equation that'll be useful for us if we know the pieces that we need to know. So it's pretty simple. We go ahead and I'm going to add, there's a few ways to do this, but this is just some simple algebra. And even though I say simple algebra, I know that lots of people get caught up on algebra. So if you don't know it off the top of your head, if you don't know how to handle algebraic situations, I recommend practicing those. I could do a video on those in the future, but I would like to stick to some more complex topics. All right, so we add the intersection to both sides, and then let's subtract the union from both sides. Could do this multiple ways. Not, like I said, I'm not going to get into all the different ways to do it, just because this is something that people really should have as sort of a second nature by this stage, and really after high school. And it's really unfortunate that we don't. It's something that's often foregone, pushed aside, thought of as meaningless, or thought of as too difficult to deal with. I'd like to change that. But anyways, so we rearrange our formula to get from here, solving for the union, to here, solving for the intersection. Let's go ahead and plug in our values here. Say that the probability of A is 0.6, probability of B 0.8, and we're going to say that the probability of the union is 0.9. Takes up most of the space. So let's go ahead and plug these in. We get 0.6 plus 0.8 minus 0.9. That gives us that the probability of the intersection is 1.4 minus 0.9, which gives us 0.5. Exactly half of the space is taken up by this intersection. Alright, let's take a look at a space with 3 sets, which we talked a bit about earlier, but let's go a bit more in depth. Here's where it starts to get much more messy, in my opinion. So, let's say we just want to look at the union of this space. Shouldn't be so bad. The probability of A union with B union with C. Right. Well, we want to take all of A, all of B, all of C. As we can see, there's quite a bit of overlap. All right. So we get the probability of A plus the probability of B plus the probability of C. But now we have to say this space we doubled up, this space we doubled up, this space we doubled up. The intersections of each individual group we have to start removing, just like with the probability of A unioned with B. So we want to remove the probability of A intersecting with B, which is right there. Want to remove the probability of A intersecting with C, right there. And finally, want to remove the problem of B intersecting with C, right there. So we caught all our in-between places. But these in-between places have an additional overlap, and that's right in the middle. This middle piece we now have to re-add because we removed it. We took away this and this and this, and with it we also took away that multiple times. So we got to put it in one more time to kind of fill in the gap. I like to think about these probabilities as kind of like a balancing game. It's weird to think about how we're having to balance our probabilities. We're going to have to add certain probabilities, then take out chunks, then re-add chunks. But with a visual, I feel like that really cements itself. It's a lot clearer than when you're just given a formula like this in a textbook and be like, okay, this is how you do it. And just as a reminder, this is how we're finding the probability of the union of sets A, B, and C. So you know what we're going to do now? We're going to throw in some numbers, make an example. Probability of A 0.22. Probability of B, 0.25. Probability of C, 0.28. Now, the thing is, for these problems, you need to know a lot of information going in. Things get messy, things get tricky, but we're going to assume that we know a bunch, and then later you can think about on your own, or we can do some more videos, do more examples on how exactly we could break down those larger problems, because you can see how they're similar. But let's just go ahead and assume that we know a lot about this situation. So the intersection of A and B, again, you say is 0.05. Intersection of A and C is 0.07. Intersection of B and C, 0.11. And the intersection of all three, A, B, and C, 0.01, which makes sense. You intersect all three and just kind of get these tiny little bits. All right, looking at our formula here, add together chunks, remove a few smaller chunks, add back in the smallest chunk. So let's start. Let's make sure we can actually see the numbers. 0.22 plus 0.25 plus 0.28. Probabilities of A, B, and C, minus 0.05 minus 0.07 minus 0.11. The probabilities of each set intersecting with one other set. And finally, we're going to add back in right on the end here, 0.01. All right, what does that get us? Well, if we add together the probabilities of A, B, and C, and then that additional 0.1, we get 0.76. Then, if we subtract the summation of these, 0.7 plus 0.11 plus 0.05, we get minus 0.23, 0.53 as our final answer. All right, sweet. That wasn't so bad. If we break it down into all those individual pieces and then combine them, again, with visual aid, it's easier to wrap your head around. But if you can't get it immediately, or if it doesn't stick, or if you're saying, oh, I gotta keep going back to formulas to figure out how this works, that's fine. Drawing a picture, though, that's a great tool, not only in statistics, also in calculus, analysis, really any sort of learning. Visual aids are great. So today we looked at a few of the basics of stats, and there's so much more to look at in the basics. So I really do thank you for watching. I can't wait to see you in future ones. I would love to do more stats videos. It's one of those things that I love to have a stats textbook on hand, be that like on my iPad or just physically in person next to me, to just have around, because even though it doesn't get as much of a reception by a lot of the math community, it has its place. It's incredibly useful, and honestly, it's pretty fun a lot of the times. But because it's its own little section of math, it can get forgotten, it can get confusing, and I frequently get questions of how to do this in stats, how to do that in stats. Who are the experts in stats? Because it is kind of niche. But yeah, that's all. Thanks for watching, and bye-bye!